All right. In the previous segment, we figured out how to go around computing, how to go about computing the gradients, right, which go into our integrals. So let's pick up there and complete the evaluation of this integral. And you will recall that the integral we were working with is the following. Integral over omega e wh comma x ea comma x dx. And using what we developed in the previous segment, we know we can write this as sum over, integral over omega e. Let me see, we can write it out as sum over a na comma c comma x, which is 2 over he, times cae. All of that is wh comma x, multiplying ea times sum over b nb comma c comma x, for which we again use 2 over he, dbe, dx, okay? But note that for dx, we could write it as dx dxc dxc. All right? And we know that dx dxc is just x comma c, which is what we computed in the previous segment to be he over 2, even for quadratic basis functions, and this comes about from the fact that we have an affine map. It also has to do with the fact that Lagrange polynomials are complete. Okay? All right. So we have this representation, and now we can write out this integral in an even simpler form. We are going to note that because of the fact that we have he over 2 here, this cancels out with that. Okay? And we can now write out this integral using what we call matrix vector notation. Okay, and in order to use matrix vector notation, let's actually set it up a little more carefully. Okay, we will use matrix vector notation, but let's do just one step before it, which is a step we've taken when we were working with linear basis functions, and that is to recognize that CAE, the DBEs are independent of C, and so too is this product EA of constants. And this remaining 2 over he. Since they are independent of position, they can be pulled out of the integral. Okay, right? So we're getting up to using matrix vector notation, but before we actually do it, let's write that integral as a sum over a and b of the following quantity. We can actually pull even EA out of that summation, right? So we can have 2 EA over HE sitting outside this summation. Okay? And then we have the sum over A and B, CAE, right? Integral over well, we'd written it up here as an integral over omega e, but using this chain rule right there, we observe that we can actually write that integral as an integral over over what? Over a different domain, right? Right, it's over omega c. Okay, now the integrand is a simple one. It is NA comma c NB comma c. Okay, dxc. All right, and I'm going to put parentheses on this integral just to make it clear that it's that's where the integral ends, and then here we have dBE. Okay, the use of matrix vector notation, as you will recall from our development of the method for linear basis functions, the use of matrix vector notation comes in to relieve us of the need to have this explicit sum. Okay, so now using matrix vector notation, here's what we get. That sum over A can be replaced by, sorry, I have an equal to sign here, right. The sum over A can be replaced by C1e, C2e, C3e. Okay, these being the degrees of freedom that interpolate the weighting function in element E. We get 2e A over HE, right? We get our integral, right? However, we get a bunch of integrals, each of which is one component of a matrix, right? Here we get integral over omega c of n1 comma c, n1 comma c. However, the integral over omega c I'm going to write explicitly as an integral from -1 to 1 over c, right? Because that is the extent of our bi-unit domain. So here I get n1 comma c, n1 comma c dxc. The second position I get integral -1 to 1 n1 comma c n2 comma c. In the third position, in the 1,3 component of this matrix, I get integral of n1 comma c n3 comma c. All right, here I get integral -1 to 1 n2 comma c n2 comma c dxc, and here I get integral -1 to 1 n2 comma c n3 comma c dxc, and here I get integral -1 to 1 n3 comma c n3 comma c dxc. What about the rest of the matrix? Right, it's symmetric. Right, so multiplying all of this, I have here, instead of the dBE, I have those represented as d1e, d2e, d3e. Okay, so this is our matrix vector representation of our left-hand side integral over an element for quadratic basis functions. What we're going to do next is actually explicitly calculate those integrals. All right, so integral -1 to 1 n1 comma c n1 comma c dxc equals integral -1 to 1, let's see, It is, let me just check what that integral is, what that derivative is. That derivative is 2c minus 1 the whole square dxc, right? 2c minus 1 is n1 comma c. Okay? All right. So we get here for this integral, we get, this is the integral minus 1 to 1, 4c square minus 4c plus 1 dxc, and observing that this is an integral from minus 1 to 1, we know that the odd terms don't survive the integral, right? It's only the even terms that survive. When we do this, we get 4c cubed over 3 plus c, limits minus 1 to 1. Okay? This is 4 over 3 plus 1 minus 4 over 3 minus 1, right? Which is 2 times 7 over 3. Let me just check this out. N1 comma c. All right, there is a 1/4 here. Okay, that's because n1 comma c is 1/2 of 2c minus 1. So we get a 1/4 here. We also get a 1/4 here. 1/4 here, right? And we get a 1/4 here. So when we carry this out, we get 7 over 6, right? Which is what I was expecting. All right, now into the next term over, right? My integral minus 1 to 1, n1 comma c, n2 comma c dxc. This is the integral minus 1 to 1, and 1 comma c we know is 1/2 times 2c minus 1. And 2 comma c, as we saw from before, is minus 2c. Okay? Integral over dxc. This is then 1/2 integral minus 1 to 1. Okay, what do we get here? We get here 2c minus 4c square. Okay, dxc, which is 1/2. Once again, we don't need to compute the odd term, right? We compute only the even term. We get 1/2, let's pull the minus sign out, we get minus 1/2 times 4c cubed over 3, limits minus 1 to 1. All right, and this turns out to be minus 2/3 times 2, which is minus 4 over 3. Okay, all right, moving on. Integral minus 1 to 1, n1 comma c, n3 comma c dxc is integral minus 1 to 1, 1/2 2c minus 1 times 1/2 2c plus 1 dxc. Okay, this is 1/4 integral minus 1 to 1 4 c square minus 1 dx, which is 1/4 times 4 c cubed over 3 minus c. The limits on this are minus 1 to 1. Okay, let me actually use square brackets here as I did previously. Which is now 1/4 times 8 over 3 minus 2, which is 1 over 6. If I'm not mistaken. Yep, right. Okay. Carrying on, let's just move on to the next slide here. So the next term we need to calculate is integral minus 1 to 1 n2 comma c n2 comma c dx, which is integral minus 1 to 1 n2 comma c is minus 2c, and we get the whole square here. Right, and this is an easy integral to carry out. It is just 4 c cubed over 3 limits minus 1 to 1, which gives us 8 over 3. All right, integral minus 1 to 1 n2 comma c n3 comma c dx. All right, that's the 2-3 term of the 2-3 component of the matrix. This is integral minus 1 to 1 minus 2c times 2c plus 1 dx, which when we carry it out is integral minus 1 to 1. Let me see, what do we get here? We get a minus 4 c square minus 2c dx, which is, as I've been doing often in this calculation, I'm missing a half here. So I get a half here. Okay, so that is 1/2. Again, using the fact that it's only the even terms that survive, we get minus 4c cubed over 3 minus 1 to 1. And when we go ahead and compute this, we get minus 4 over 3. The very last term to be computed here is the integral minus 1 to 1. The very last component is integral minus 1 to 1 n3 comma c n3 comma c dx, which is the integral minus 1 to 1. We pick up a 1 over 4, and here we get 2c plus 1 the whole square, right? And that is because n3 comma c is just 1/2 2c plus 1. All right, so here we get 1 over 4 integral minus 1 to 1 4c square plus 4c plus 1 dx, right? 1/4 4c cubed over 3 plus c. And limits of the integration are minus 1 to 1. And when we compute this, we get 1/4 of 8/3 plus 2, which is right, 7/6. All right, excellent. Now, collecting results, what we get is the following. We set out to compute integral over omega e wh comma x sigma h a dx. Upon first substituting the constitutive relation for sigma h, then using our basis functions to write out the fields and their gradients, and then going ahead and doing the computation, right, doing an explicit integral over c, integration over c, we get the following. We get c1e, c2e, c3e, right, which is our vector representation of the nodal degrees of freedom of the weighting function. Okay, 2e a over he, and here we get our matrix, which we've just computed, and we've just computed it to be 7/6 minus 4/3, 1/6, 8/3 minus 4/3, 7/6. It's symmetric, but now let's just explicitly fill it in just this time. And for our vector representation of the nodal degrees of freedom of the trial solution, we have d1e, d2e, d3e. Okay, now as we observed before for the case of linear basis functions and linear elements, right, two noded linear elements, this is what we will denote as ke, right, our element stiffness matrix. All right, this would be a great place to end this segment.